Right. Well, I'd like to thank the organizers for the chance to speak in this seminar. I'm sure we all sat through a lot of Zoom seminars last year. I mean, some of them I hope will continue. I mean, like this one, you know, it's been a good experience. So I'm very, very keen to continue with these kinds of multinational seminars. Okay, so when I was invited to talk, I had in mind a talk which at some point I decided was not the right talk. And then I thought of another one, and that sort of depended on a theorem that didn't work out. So in the end, I decided to give a sort of composite talk, which is partly historical and partly based on fairly recent work with Gerd Laurers and Jan Holtz. So the first half of this is sort of historical, not in any professional historian type sense, but to give you some sort of overview of what has been done with MSP in the last half century or so. Okay, so, oh, wait. I know. Sorry, I have to learn to juggle. Oh no, what have I done? I've done something crazy. Okay, yes. But I can't figure out how to page on. What am I doing? No, that's wrong. Sorry, I'm having a problem with my sharing. Resume share. Okay. That's all right. Oh, why can't I page up? Right. Okay. Yeah. So, what is MSP, first of all? Well, I'm sure everybody's familiar with things like MU. So it's based on the compact symplectic groups, SPN. These are the things that preserve the sort of quaternionic Hermitian form on quaternionic vector spaces. So they fit, they're subgroups of the unitary group of size 2n. Actually, they sit inside the special unitary group. They also sit inside the size 4n orthogonal group or the special orthogonal group. So these are sort of classical groups. And if you fit them all together, you get an infinite loop space, BSP, and it comes with a naturally infinity map to BO, so you can tomify and you get an infinity ring spectrum. All of that is sort of very, very standard. Now, back in the 1950s and 60s, people following the work of Tom and then Milner and Wall and so on, there was a huge industry of computing cobordism groups, which are the same thing as homotopy groups of Tom spectra. And by and large, the classical cases were all sorted out by, I guess, the early 70s. I'm not sure the precise dates. The one thing, well, the two examples that stood out were MSP and, well, I guess you could call it the trivial group, framed bordism, which of course is the homotopy groups of spheres. All of the other classical cases were sort of understood fairly well by the early 1970s. Of course, later things like MO8 came along and string bordism and so on, but you know, the classical cases, except for MSP and frame bordism, were pretty well understood maybe half a century ago. Now, the case of MSP, I'm not sure who, I guess the middle 1960s, people like Peter Landweber, Bob Stong, Arunas Levicius, and a student of his called David Siegel, they all began to look very seriously at MSP from a various points of view, sort of geometric and using the atom spectral sequence. But I guess it became clear very early that the atom spectral sequence was not going to be an easy calculation. I guess Stan Kochman started working on this in round about 1972, 3, 4, that kind of time. He finally, over several decades, published 3 AMS memoirs where he calculates the whole classical atom spectral sequence at the prime 2. And, well, the simplest thing to say is the answer is incredibly complicated. For example, there is lots of 2 torsion of arbitrarily high 2 exponent. On the other hand, the nilpotence theorems tell you the torsion is all nilpotent, so you have some sort of understanding of that, but there's also a lot of free stuff in there. So, you know, there's no nice description. For those who wonder about odd primes, well, at an odd prime, localized in an odd prime, you just get a wedge of BPs. So there's no real interest in working at odd primes. So we'll assume from now on that everything is 2 local, even if I don't say it. Sorry, hit the wrong thing. Yeah. So various people like Connor and, well, Ed Floyd, I don't know if Connor was involved. Ed Floyd did some work, and he actually did some interesting things. He looked at the image of pi star of MSP in pi star of MO, and he identified a subring of the homotopy of MO, which was an upper bound for the image of MSP. And of course, the homology of MO is totally detected in mod 2 homology. So in effect, he was really trying to identify the image of the homotopy of MSP in its mod 2 homology. I mean, that's essentially the same question. And he came up with this lovely subring of the homology of MSP, which was an upper bound. And then later, Kochman actually showed that that was, in fact, realized. So combining the two ends, you got a description of that. And it turns out that the mod 2 Hurewicz image is not trivial. Now, this sort of came up, those of you that have read Stuart Priddy's paper on constructing BP, you may remember he actually also tried to do something similar with MSP, and he sort of did a construction and showed it sort of worked up to about dimension 32. And that is sort of essentially the same. I mean, he was encountering the same phenomenon, that this image is non-trivial. And Peter May and I worked with things called minimal atomic spectra about 20 years ago. And what that says is that MSP is not minimal atomic, whereas, for example, BP is, but MU is not. So being minimal atomic is a really strong condition. It's stronger than just being atomic, in fact. So this tells you that once you get up to degree 32 and beyond, you see obstructions to minimal atomicness. Now, if you put more structure in, I'm sorry, I'm trying to think how I can move. I've got, that's better, right. On the other hand, MSP has extra structure. It's E infinity. It's an E infinity ring spectrum. And if you think about that structure, there is an analog of the Hurewicz homomorphism, but in the E infinity world, and it involves topological André-Quillen homology with mod 2 coefficients. And there is a kind of Hurewicz homomorphism for this. And TAQ of MSP turns out to be something that we understand. It's the same thing as the mod 2 homology of connective KO with a degree shift of 4. It starts in degree 4. And if you look at the Hurewicz image in the infinity world, it turns out it's 0. Now, that means as an E infinity ring spectrum, it really is rigid in this very strong sense of minimal atomic. There's a notion of E infinity minimal atomic. Now, that's a stronger statement, or it's assuming more structure than similar results that people like Kochman proved about a weaker notion of irreducible ring spectrum. It's an E infinity statement rather than just a homotopical ring spectrum statement. Okay, so that's some things that are a sort of mix of old and new. Now, there's a question which I still find very interesting, and I'm not sure if anyone has really looked at this since Kochman's work. Stan Kochman, in a paper published in an AMS memoir from about 20 years ago, observe that if you look at the image of the homotopy of spheres in MSP and think in terms of the mod 2 Adams filtration, not much survives. In fact, the only things that really survive, apart from pi 0, are the Adams mu family. Now, of course, that doesn't say that the image is actually 0. It just says what's going to happen is that some things may not go to 0, but they shift Adams filtration from where they are in the homotopy of spheres. So, you know, that's a little bit more subtle than just saying the image is 0, because you may very well have things, you know, which are still non-zero in MSP, but from the point of view of Adams filtration, they're shifted up. So that is, as far as I know, still not completely understood. On the other hand, in the early 1970s, Nigel Ray, who was my advisor, actually did prove a very strong statement about the image of J. He showed that apart from Ada, the image of J, it maps into MSP and it almost all dies. Apart from Ada, everything dies. Now, of course, you might guess that that's really something to do with phenomena in K-theory, and in particular, the K-localization. So I'm going to come back to that point later when talking about much more recent results. Okay, now another thing that Nigel Ray did, which really was probably the most important thing, was he produced an infinite family of multiplicatively indecomposable elements. There's my first typo. These occur in degrees which are 5 mod 8 or minus 3 mod 8. And these are elements of order 2. And the construction of these is an interesting geometric construction, which I won't explain, but you know, they have their origins in some interesting geometric phenomenon. It's now, given a lot of work that's gone on since the early 70s, it's now very clear that these are, in some sense, the most important things. Everything sort of flows from a knowledge of these elements in some way or another. So these are extremely important elements. To give you one example of their properties, if you want to understand them, you can look at their image in K homology. So you can look at the KO Horevich homomorphism, and these turn out to map non-zero. Now, you have to think a little bit about what that's saying, but remember, in the K homology of MSP is a polynomial algebra over KO star. So all of the torsion in there is torsion of exact order 2. And these things are detected somehow by terms involving the things in 1 and 2 mod 8. So in fact, that led to a conjecture which for a long time seemed reasonable, that all of the torsion might be detected in this way. That would be a sort of Hattori-Stong theorem for MSP. And this turns out to be completely wrong because, for example, there's torsion of order 4, indeed arbitrary powers of 2.
Excuse me, Andy, can I ask a question? How is it that the torsion in KO star MSP is concentrated in dimensions 1 and 2 mod 8?
Yeah, but the generators here are in degrees divisible by 4. So this is polynomial generators in degrees divisible by 4. So these guys, you know, there will be a tagging term, which is the thing in 8k plus 1 times something in a generator which is in 4 mod 8.
Okay, right.
So yeah, you're right. I mean, that's a bit confusing at first, but that's what's going on. There's that sort of degree 4 shift. Yeah. Okay. Now, I was always very interested in this result, and in fact, actually, I maybe afterwards I'll tell a story about Doug and his influence on my life, which has to do with this. If you remember, these are elements, so you can pull them back to MSP smash the Moore spectrum, and of course there's a degree shift there. So you get a bunch of elements in MSP smash in the homotopy of MSP smash the mod 2 Moore space. And then you can just map that into BP homology. And I wrote a paper, it was actually in the proceedings of the Adams Memorial Conference from 30 odd years ago. If you look at the ones which are 3 less than powers of 2, and you take the corresponding phi tilde things, take this BP Hurewicz homomorphism, they have a really nice expression in terms of 2 of the V's mod the next invariant ideal down and decomposables. Now, I sort of interpret this as, in some sense, saying these should be viewed as transchromatic in some sense, because they sort of mix the different periodicity layers. Now, I don't at the moment have anything deeper to say about that, but I personally think that MSP is an interesting object, partly because it has a lot of sort of transchromatic structure. And this is my main piece of evidence for that. Okay. All right. So that's something that has been around for a while. Now, I want to mention, before I get on to the main recent thing, something I proved last year. Doug's localization paper, I'm not sure if it actually mentions MSP, but there's a sort of missing result. In his paper, you can see for sort of general reasons that the Bausfield classes of the sphere and MSP and MU sort of are related by these equalities. And of course, if you localize at 2, you can replace MU by BP. And as far as I know, there is no previously published statement sharpening up those weak inequalities. So I put a paper on the archive at the beginning of this year about this, and I claim that in fact these are strict inequalities. So that's a bit of recent gap filling in the literature. I mean, it's possible Doug had a proof of this that he never published, and maybe other people have thought about it. But
Andy, what happens if we smash instead with more spectra, some generalized more spectra? Is there a corresponding formula or anything known?
Bausfield classes.
Huh?
Do you mean for the Bausfield classes?
No, I mean in the previous page. I'm sorry, I'm still stuck on the previous page.
I haven't really thought about that, but that's the kind of thing that when I say it's transchromatic, you might expect, to get. Maybe we can talk about this afterwards. I mean, that's exactly the sort of question I would like to think about. And, I'm hoping to spend some time in Bonn next year and talk to Toby Bartle about this. But yeah, maybe we can talk about that afterwards. Yeah. Is that okay?
Yeah, thank you.
Yeah. Okay, so I want to now shift focus and start thinking a little bit about Bausfield localizations. In fact, the K-theory localizations. So remember, we're working mainly at the prime 2, so let's just assume that. And they're essentially, well, there are 2 Bausfield localizations you can think of here. One is K-theory itself, 2 locally, which you could think of as KU or KO, doesn't really matter. Or you can take the mod P version, K1 local, which of course you get by 2 completing the K-theory localization. And of course, there's a big story about this, and you can read about this in Bausfield's paper and Doug's localization paper. The homotopy groups of the K-local sphere, well, there are sort of 2 bits. One is the bits that look like the image of J. These are these sort of finite summands, but in fact, they occur in sort of mirror pairs. You get the positive degree stuff, but you also get a reflection of it in negative degrees. So the image of J sort of appears here in 2 different guises on either side of 0. So the indexing here includes negative S's. But you also get, well, in degree 0, you get a copy of 2 local integers, but you also get something really weird in degree -2. You get a Q mod Z localized at 2. And that's actually the thing we're really going to be talking about. So that bit is in there, and you can't ignore it. But something else to say here is that the classical image of J is, as I hinted, detected by these sort of positive values of S summands that occur. Okay. Now, the multiplicative structure is important, obviously, and in particular, this is something you see in Doug's paper, the pairing between the sort of mirror image of J groups in positive and negative degrees. If you look at the 8s-1 and -1, those pair to give you an injective group homomorphism into that Z mod to infinity summand. And that's actually an injection. So of course, what that's really is that the images of these exhaust this, because these tensor products are really just cyclic groups, and their orders grow as S is divisible by higher and higher power of 2, then you get bigger and bigger cyclic groups appearing. So you basically exhaust this infinite torsion group with the images of those products. That's actually a useful thing to know, because I'm going to use that later on. Okay, now if you pass to the K1 localization, that basically completion, and the finite summands don't change, but in degree 0 you get a two-adic integers appearing, because that's the completion of the two local integers. But something more complicated happens with that Z mod to infinity summand. When you to complete, that gets sort of compactified, and it becomes a copy of the two adics, but it shifts up a degree. So that now lives in degree -1, and you don't get anything in -2. Now, there is a standard name for this generator. It's usually called zeta or zeta sub 2, and that's again going to come up in a while. So there's a sort of compactification or completion going on there, which sort of explains that jump in degree. And of course, the real origins of that go back to things in Bousfield's paper, where he talks about how to think about completions in terms of X completions and so on. So there's this kind of functorial short exact sequence which tells you how to go from the K local to the K1 local homotopy groups. Okay. All right. Yeah. All right. Now, okay, so we've got basic knowledge of the K-local sphere, and of course we can K-localize MSP, and we get any infinity morphism between them, because localization preserves the infinity structures. So if you look at what this does, you end up with this huge diagram. So at the top here, what I've got is these two, I've missed off a K. There should probably be a K localization in there. Well, I guess it doesn't really matter. I'm thinking of S here as being positive. So up here, you've got these two homotopy groups pairing. That takes you into this image of mu S inside of the homotopy of the K local sphere. And then you can go into the analogous thing inside of the K localization SP. Of course, you can also map the unstable homotopy of SO into the homotopy of spheres. That's the J homomorphism. And, well, Nigel Ray tells you that if you go all the way down here on the left, that map is null, right? He proved that the image of J in these degrees anyway goes to 0. I mean, the only time it doesn't is when you're looking at pi 1. So in fact, going around this diagram, you get 0. So using the thing I said about the injectivity of the pairing maps in those degrees, so this actually tells you that the pairing at the K local level actually kills the Q mod Z in degree -2, right? Now, that of course is using Nigel's Nigel's statement about the image of J. Now, if you pass to the K1 local story, you can use that Bowes-Field exact sequence to show that, in fact, zeta must also die. So when you sort of transplant this to pi-1 of the K1 local versions, you see that zeta goes to 0. Okay. Now, remember, we're working in the infinity world here. So this says in the language of Marcus Zimmerch that MSP K1 locally has characteristic zeta. He developed this notion of characteristic of a ring spectrum, in the infinity ring spectrum, and in particular, this sort of example was one he looked at. So we're looking at an infinity K1 local ring spectrum where this image, this special element in the sphere under the unit map dies. So that's sort of a characteristic zeta kind of situation. Okay. All right. All right. Well, now I want to start talking about things I've been talking with Gerd Lauwers and Jan Holtz about. Jan was a student of Gerd who wrote his thesis. Well, his exam was at the beginning of this year, and I think he's not in academia anymore, but he worked out a lot of this about MSP. So I want to start talking a little bit more about MSP from a homotopical point of view. And in particular, we know that nu and sigma go to 0 in the homotopy of MSP. So in the infinity world, you can form a sort of double mapping cone. This double slash notation is, for people who do this kind of thing, is now fairly standard. This really doesn't mean maybe what you think it means. It means you work in the world of the infinity ring spectra. You attach a cone to kill nu and a cone to kill sigma by some kind of a junction push-out type diagram, but you make the bottom cells of the usual mapping cones coincide with the unit in the ring spectrum. So it's a little bit more collapsed than you might think. It's not just like the free gadget on the wedge of the two mapping cones. You have to identify the bottom of cells of those to the unit. So at least that's what I mean by it. Other people may mean something slightly different. So, of course, the fact that nu and sigma die means you should have some sort of infinity map into MSP. And the first thing to note about this is that in some sense, this is already a 9 equivalence. It's an equivalence up to degree 8. Now, you can interpret that in two slightly different ways. One of them is you forget the infinity structure. Just think about these as spectra with a map, and you could realize them with some kind of CW structure. So you can do it minimally. You take a minimal number of two local cells in some sense, and then you compare them to homology, and you discover that these are equivalent. So for those who know about the homology of this double slash thing, it's roughly speaking, it's going to have a generator in degree 4, a generator in degree 8 for the cones, and then you take the sort of free Dyalashoff monomials on those things. So it's a kind of free algebra where you take a 4 and an 8 dimensional generator, admissible Dyalashoff monomials, and you just take the huge polynomial algebra. But you don't get anything up to degree 8. You don't get anything except just the ordinary products of the 4 cell with itself and the 8 cells. So there's no Dyalashoff stuff up to degree. First thing that occurs is in degree 9, right? So forgetting the infinity structure, you can think of this as a 9 equivalence. But if you do want to think about the infinity structures, which is obviously something you might want to do, given that these are infinity, again, there's a way of thinking about cell structures in the infinity world. Again, you attach cells in the infinity way. You could talk about CW structures, and you can talk about minimal structures. And again, you can check what's going on in some sort of homology theory, which is appropriate to the infinity world. And that is, again, topological Andrei. And again, you discover it's a 9 equivalence. Now, just to sort of make things a little bit more explicit, so I've sort of tried to give some idea of what these various things look like. The homology of this double cone thing, you know, it's as I said earlier, it's got a unit, and then it's got a 4-cell, it's square, and then 8-cell, and then you start getting all sorts of junk higher up, Dilashoff type stuff. What does the homology of MSP look like? Well, it's got a 4-dimensional generator, and then an 8-dimensional generator, and then 12, and so on. But up to degree 8, you just get 1, Q, Q1, Q1 squared, Q2, and then you get a gap of 4 until you get the next stuff, and so on. What about TAQ? Well, TAQ of the double cone is as simple as you might guess. It's just got 2 generators, 1 in 4, 1 in 8. There's nothing else. You don't see any of the Dilashoff monomials. Those all go to 0 under the map. There is a map from ordinary homology into TAQ. It kills decomposables and Dilashoff monomials. So there's not much else that can survive. You don't see the unit. So just 2 things. TAQ of MSP, that's the homology of connective KO with a degree 4 shift. So in the 2 dimensions we want, you've got a 4-dimensional thing, which is the suspension of 1, and you've got psi1 to the 4th, which is shifted up to, so it's in degree 8. So you're sort of seeing the bottom 2 cells, but of course there's higher up stuff, right? But none of that detects homotopy. So that's sort of what's going on in the different cell pictures. Okay, when am I supposed to finish? Is it 45 minutes? So about
So you have
10 minutes or so? Yeah. Okay, right. All right. No, actually, that, you know, if you really start thinking about this, that just think about so supposing you just cone off nu and look at the sort of E infinity cone of nu. Forget about the sigma part. What's the cell structure there? Well, in low degrees, you've got the unit at the bottom, then you've got a 4-cell with a square 4 in homology, and there's a nu attaching. The square also has a square 8 on it down to the bottom. So this is meant to be going on in the homology of this E infinity cone on nu. But you might sort of, and I certainly guessed this when I first started thinking about this, that there was a sigma attaching you to the bottom, but that's not quite right. What actually is going on is that the 8-cell is attached to the 4-cell by something like sigma plus a coextension of twice nu. It's a little bit more complicated than you might envisage. Sigma itself does not die here, right? Whereas, of course, you can cone off sigma afterwards, and that gives you another 8-cell. But if you just cone off nu, you're not at that stage killing sigma, even though there's a square 8 down to the bottom. It's a little bit kind of subtle to sort that out. If you want to check this, you can do it in BP homology or maybe K homology if you know, using Adams operations or whatever. So you know, that's sort of very old-fashioned kind of homotopy theory, and it's lurking around inside of this E infinity coning construction. Now, so what's interesting is, of course, that statement about 9 equivalences. It's saying that the way you have to attach that extra, that second polynomial generator of MSP has to do with killing sigma, right? So, you know, there's not much difference between these 2 things up to that degree. And the role of the generator I called Q2, in some sense, is to kill sigma, right? That's the way I like to think about it. Going into the K-local world, well, this was something that Jan actually did in his thesis. He proved that, in fact, this element zeta, when you take the unit into this double mapping cone localized, zeta also goes to 0. So this thing itself has characteristic zeta. Now, his approach to proving this was to use something that, what have I done? Right, was to use something that certainly Gerd Lauwers has used in papers to do similar things. You look in K theory. It doesn't really matter whether you do this in KO or KU, and sort of take a suitable completion of that. And inside of the 0 degree K homology, appropriately completed, you find an element called an Artin-Schreier class or Artin-Schreier element, and this is sort of characterized by the way that the Adams operation psi9 acts. It basically acts by sending it to itself plus 1. And if you know about how the zeta class arises in a sort of K1 local resolution for the sphere, you'll see that that's exactly what's needed to kill zeta. So this Artin-Schreier class is something you build, and what you do is you write down something, take a log series, which of course you need to check converges in some sense, some sort of two-adic sense, and maybe put a correction factor in, and then you've got an Artin-Schreier class. So he used that technology to do this. Now, once you've done that, you can read off using some results of Lauwers that were from older work to prove various things that follow. For example, in the infinity world, this spectrum splits. It splits as a product of the K1 local sphere with zeta killed with a load of other junk. I won't say what this is, but it's some big mass of stuff. And a similar story holds for MSP. Again, it's a sort of multiplicative splitting. All of this is meant to be interpreted in the K1 local world. Okay. Now, in fact, I didn't realize until a week or so ago that actually I'd proved this already in a paper without sort of thinking about the zeta characteristic business, because I actually proved in a very different way using theta algebra structures that, for example, if you cone nu and then work K1 locally, what you get is a product of a bunch of, that sigma should be a big sigma, a bunch of suspensions of KOs. The technology for doing that was to use Hopkins' idea of theta algebras and prove that two theta algebras were actually isomorphic. And then there was a kind of Milner-Moore type argument, which Gerd had used. So that sort of result, you can get it in various ways. But once you've got that, you know that zeta dies in that spectrum. So it actually already dies when you've killed off nu, in fact. You don't have to kill both nu and sigma. Killing nu is enough to kill zeta. That's slightly surprising given what was in Jan's thesis, in fact. Okay. Now, about a week ago, Gerd and I were having a Zoom chat about this and trying to sort of, we were trying to sort of think about how to write this down efficiently. And then we both sort of realized, I think, simultaneously that actually the way Jan did this was to work with manifolds, construct manifold properties and build the Artin-Schreier class essentially from geometry, right? But we both realized that, in fact, in the end, it's really a homotopy theoretic construction. And with a bit of sort of messing around with this, we came up with a result, and I'm pretty sure this is correct, although obviously it's not written up yet. So I'm stating this for both the prime 2 and for odd primes, and I'm only going to state this for a version based on the classical connective sphere spectrum. However, you can replace the generators by these negative image of J things in the K local sphere, and there's a similar kind of statement. So, so what's the story at odd primes? Well, okay. No, what's the story at 2? Right, the story at 2 is that if you take a generator of the image of J in a degree which is 1 less than a multiple of 4, so that's 4 mod 8 or, sorry, 3 mod 8 or 7 mod 8, and And then you cone that off in the infinity world and pass to a completed version of K theory, then you can find an Artin-Schreier class, Artin-Schreier element. So in particular, that says in the infinity world, coning the image of J and K1 localizing, that spectrum has characteristic zeta. Okay. Now, if you work at an odd prime, well, it's actually rather simpler to do this at an odd prime. The interesting dimensions here are the ones which are 1 less than a multiple of 2 times p minus 1. In those degrees, you get the cyclic groups of order some power of p, and the same thing happens. The p completed K theory of the C infinity mapping cone has an Artin-Schreier class, so has characteristic zeta. So that's a completely uniform picture, and it's actually very easy. If, for example, you can go back to Adams's J of X4 paper and essentially use what's in there to do this calculation. What, of course, Adams doesn't do is work out the Artin-Schreier element, because for that you have to take something which looks like 1 mod 2 in degree 0 or 1 mod p in degree 0, and then take some kind of log series of it with a correction factor. So that involves some kind of infinite series, some sort of convergent series in the p-adic world, which certainly Frank didn't talk about. But the basic thing that you start with is what comes out of his E-invariant calculations in J of X4. The way I did them was slightly different, but I mean, that's all you need to do, really. So the input for doing this is really back in J of X4. Now, various things follow from this. So what follows from this? Well, in the 2' primary case, of course, you can now see that if you just cone nu or sigma, I'm sorry, the last one should have both nu and sigma in it. Sorry, I missed out the nu in that last term. So either you cone nu, or you cone sigma, or you cone both nu and sigma. Any one of those already, zeta has gone to 0. So they've already got characteristic 0. Now, you might wonder, what about eta? Because eta sort of hasn't really appeared in any of this. And it is, of course, an element. Well, here's something interesting is going on in the homotopy theory at the very bottom skeleton of the E-infinity cone on eta. If you think about what you've got a 0 cell, a 2 cell, and a 4 cell. Again, you've got a square 2 from the 2 to the 0 generators. You've also got a square 4 from the square of the 2-dimensional class down to the bottom. And in fact, that really does detect an attaching map, which must be essentially nu. And the reason is that you don't really have any other possibility for a map from the 3-sphere to the mapping cone of eta. So you really are attaching that 4 cell down to the bottom by something like nu or some mod 2 unit times nu. So that means that there is actually a map from S/nu into S/eta. So now you can use naturality to show that, in fact, zeta is already dead in S/eta K1 locally. So you don't need to do a separate calculation for that, right? What I would like to prove is something a little bit like this, replacing eta by Adams's mu element in 8K plus 1. But that sort of depends on, I mean, to try to use the same argument would depend on you knowing, for example, that nu times mu 8K plus 1 was actually 0. And I'm not sure if that's actually known to, maybe it is, maybe Doug knows. Is that actually true in homotopy of spheres? It's true K locally, but...
Say that again. What?
So if you take one of the Adams mu elements, right, in 8K plus 1, is it true that nu times that element is actually 0 in spheres? I know it's true K locally, but
That seems quite likely because it's up near the atoms vanishing line and the atoms.
yeah, that's right. That was my guess, but I mean, I don't know. Yeah, so if that's true, then I think you can make this kind of argument work for those if you cone those off as well. But I mean, that's a minor tweak, but that sort of depends on a fact which may or may not be true in old-fashioned homotopy theory. Okay, so I think it's pretty much the time I should finish. So thank you for listening. And I have put a list of references, which some of them are quite old, some of them are relatively new. Anybody who wants it. Now, I did put, maybe I'll do it again because I'm not sure if everybody has seen this in the chat. I put in the chat, oh, right, somebody's put this in for me, right, Hannah. Yeah, if you want to get a copy of the slides, you can download a more reader-friendly version from that link, yeah. Okay, well, thank you.
Let's thank Candy for the great talk.